Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is the second video in a series on L'Hopital's rule in indeterminate forms. I've just finished talking about what indeterminate forms are. Now let's dive into L'Hopital's rule itself, which is how you deal with indeterminate forms in calculus. So here is what I've been promising to talk about. Recall that our ultimate goal with the recent materials to accurately graph curves. Critical in this process are the investigations of end behavior and the function's behavior near vertical asymptotes. These investigations often lead to indeterminate forms. Now, before I go to that next paragraph, I just want to showcase what I mean by this. So when you're graphing something using calculus, you need to figure out what does that graph look like at the endpoints and near asymptotes. So let's say that we had a vertical asymptote there, as sloppy as that is, and let's say we have this end behavior like that. So maybe on one side we have some type of horizontal asymptote at, let's say, y equals 3, and on the other side we have what we would call a slant or oblique asymptote that follows some weird behavior. So I'd like to be able to determine, and by the way, I think that this was supposed to be a vertical asymptote here. Sorry about that. That's supposed to be a vertical asymptote, and my y-axis was supposed to be like, let's pretend there or something like that. Anyhow, and that would mean, by the way, that we go all the way there. So to determine this, you have to take the limit as x goes to infinity to figure out what your horizontal asymptote is, and as x goes to negative infinity to figure out what your oblique asymptote is. When you do that, those limits as x goes to infinity might lead to forms like 0 over 0 or infinity over infinity or infinity minus infinity, something like that. And because of that, we have to invent a way to evaluate those limits. We really want to know what those curves look like at the edges of our graph, or in other words, we need to determine the end behavior of the function. Also, if you look at the central area where we have a vertical asymptote, the behavior of the function near the vertical asymptote is very important for us to find out, because we want to know, is our function rising as x approaches that number from the left? Is the function falling as x approaches that number from the right? And that's critical for an accurate graph. Now let's consider the functions f of x is equal to e to the x minus 1 and g of x is equal to x. Now, as x goes to infinity, both these functions definitely tend to infinity. That's fine. But what about the functions' ratios? In other words, what about the limit as x goes to infinity of e to the x minus 1 over x? Well, some students would argue it's obvious this goes to infinity. The word obvious should be taken out of any math course. You don't want to say something is obvious unless you can prove it. If you can prove that this goes to infinity, then maybe for you it is obvious. But most students can't prove that that goes to infinity. Instead, they just say, well, look, the top is so powerful and the bottom not so powerful, so therefore this must run off to infinity. While it does, that is not a proper justification. That is just hand waving, is what we'd call that in mathematics, where you just wave your hands like a magician and say, looky, looky, I've made something magic happen. This goes to infinity without telling me why. So that's the issue with that type of statement. I would agree, by the way, it does go to infinity. And as well, the limit as x goes to infinity of x over e to the x minus 1, that'll go to 0, but me just saying that is not enough. I should be able to prove that it goes to 0. Also, let's consider what happens as x goes to 0 for both of these functions. We know that as x goes to 0, e to the x minus 1 will go to 1 minus 1 or 0, and g of x, which is equal to x, will go to 0. So if you look at the limit as x goes to 0 of e to the x minus 1 over x, that's going to be 0 over 0. Likewise, if you look at the limit as x goes to 0 of x over e to the x minus 1, that will also go to 0 over 0. So we have two very popular indeterminate forms that we're looking at here. The infinity over infinity form and the 0 over 0 form. These are actually the two most popular and most important indeterminate forms. So again, how do we determine those ratios? And the secret is in how students would normally argue this, actually. So your intuition of saying, well, the top is more powerful than the bottom, or the numerator approaches infinity faster than the denominator in this case, is a good intuitive way of knowing how L'Hopital's rule works. L'Hopital's rule says, listen, if you got a function that's heading to infinity, and you have another function that's heading to infinity, and you're taking their ratio like we are there, well, if you take a look at a graph of e to the x minus 1, let me go ahead and just quickly jot down a graph. So this is a graph of e to the x minus 1, and if you were to graph y equals x, you could see that y equals x, and this is not a super accurate graph, but good enough. You can see that definitely the black curve, which is y is equal to e to the x minus 1, you can see that's jumping off to infinity much faster than x is. However, if we're just looking at their values, infinity over infinity, it's hard to say what that ratio is going to become. So if somebody were to mechanically just look at this, well, it's infinity over infinity, that doesn't tell you very much. But if you do a little more investigation and look at how quickly something's rushing off to infinity versus how quickly something else is rushing off to infinity, you might be able to determine something from that. And that is the ultimate idea behind L'Hopital's rule, is comparing how quickly they're going to infinities. And here is L'Hopital's rule in all of its glory and all of its glorious form here. It's L'Hopital's, not Hospitals, it's L'Hopital's. And you suppose you're given two functions that are both differentiable because you need to take their derivatives. And also suppose that g prime is not identically equal to 0. In other words, when you take the derivative of g, hopefully it's non-zero, okay? And suppose those functions are differentiable and that g prime is not 0 on a neighborhood centered at a. Now remember what I had mentioned early on in my lecture series for differential calculus. Whenever I say the word neighborhood, I really mean a punctured open neighborhood. That means that a need not be included. So x need not be a, need not equal a. So that's okay. We're taking a limit as x approaches a. So x doesn't need to actually be a. All right. So if the limit as x approaches a of f of x over g of x is an indeterminate form of the type 0 over 0 or infinity over infinity, and it can only be one of those two forms, it can't be any other form, then that limit is equivalent to the limit as x approaches a of f prime of x over g prime of x. This guy right here. So in other words, you can determine the value of the limit by looking at how quickly the upper function is approaching, let's say 0, and compare that to how quickly the lower function, which is g, is approaching 0. So compare their rates if that limit exists, which is, by the way, always the caveat when you're talking about limits. So I like Calc 1 because you end up looping around back to the beginning of the material by the time you get to the end of the course, because you start talking about limits all over again. Critical in this conversation is that the limit has to be, or this limit right here of f over g, has to be indeterminate of form 0 over 0 or infinity over infinity. Now, I was going to prove this theorem, honestly, but as I started writing out kind of how I wanted the proof to go, I realized it's going to be a little more wordy and challenging to follow and almost not worth it. In fact, it's really not worth it, because I think that a lot of people would just get lost on the technical details of the proof itself. So instead, we'll move forward with the agreement that if you want to see a proof of this, either I'll make a video for it later on, or it's usually in a calculus book. It's sometimes in a calculus book. It's sort of a higher level, so it may not be in every calculus book. If you've watched my videos in the past on theorems and stuff like that, usually I do not include examples within a theorem video, but this one's short enough that I figure it's nice to see how L'Hopital's rule works. And since we were writing down those limits earlier of e to the x minus 1 over x, that type of thing, I think it's best to go ahead and just use L'Hopital's to evaluate those limits. So here we go. Let's use L'Hopital's to evaluate the limit as x goes to infinity of e to the x minus 1 over x. Before I even evaluate it, I will note that it is actually of the form infinity over infinity. That's as x goes to infinity, this ratio approaches infinity over infinity. And right now I can't use algebra to simplify this. So I'm pretty much stuck at this point, and I need to use some new rule called L'Hopital's rule. You will see that every time I use L'Hopital's rule, I do this. I say that equals, and then I have an L with LH, right? And the reason why is because I just want to let the reader know that I am now using L'Hopital's rule. And by L'Hopital's rule, this should equal the limit as x goes to infinity of the derivative of the numerator, which is going to be e to the x, divided by the derivative of the denominator, which is 1. I often joke in class when I teach this that L'Hopital's rule is what everybody wanted the quotient rule to be. Everybody wants the quotient rule just to be the derivative of the numerator divided by the derivative of the denominator, but we know that's not the quotient rule. But that's actually L'Hopital's rule. So taking this limit, you can see it will become infinite. Now, something I do need to state here about L'Hopital's rule and using it and then getting infinities. The theorem for L'Hopital's rule says specifically that our limit that we're dealing with, if it is indeterminate of the form 0 over 0 or infinity over infinity, we could trade it out for the limit of f prime over g prime, as long as that limit exists. And I've made a big stink about this early on in my courses, also in this video series, that when I say a limit exists, it means it's either finite or infinite, but it exists. The only time a limit does not exist is if it's just doesn't exist, if it's not finite or if it's not infinite. In other words, like the sine. The sine as x goes to infinity doesn't exist because it just wiggles back and forth forever. It doesn't become finite, nor does it become infinite, so it doesn't exist. But a limit that becomes infinite, we still say that limit exists, it's just infinite. A lot of theorems rely upon limits existing and being finite. But that's not this theorem. This theorem relies just upon the limit existing, so it can actually become infinite. We can use L'Hopital's rule when the output is infinity or negative infinity. All right, going back to our list here, I actually included this second one, which is exactly like the first, right? 1 over x times e to the x minus 1 is exactly the same as the first limit there. But the reason why I did it is because I want to highlight this idea of where we're going to be heading. If you were to just look at it as written, this first part is approaching 0 and the second part is approaching infinity. So as written, it's the form 0 times infinity. And we cannot use L'Hopital's rule on it. But magically, we can easily use L'Hopital's rule once you rewrite it. So you cannot use L'Hopital's rule as it's written here, but once you rewrite it as the limit as x goes to infinity of e to the x minus 1 over x, now this is L'Hopital's, it's indeterminate of the form infinity over infinity. And you can now use L'Hopital's rule. And we already just did this. It's just infinity. But I just want to make that note because I think a lot of people, because it's one of the most popular and dangerous forms, 0 times infinity. So whenever you have that form, you want to try to finagle it and rewrite it as infinity over infinity. We'll do some examples like that in the next video. The next one, limit as x goes to infinity of x over e to the x minus 1. Well, that numerator is approaching infinity. That denominator, it is also approaching infinity, so I can use L'Hopital's. And by L'Hopital's, we have the limit as x goes to infinity of the derivative of the numerator, which is 1, over the derivative of the denominator, which is just e to the x. As x goes to infinity, that's 1 over an infinite number, or 0. So here's an example. We've seen 2 examples now of infinities over infinities, but one ratio approached infinity, the other approaches 0. So this is a good justification as to show that not all infinities over infinities are the same. Now let's take a look at as x is approaching 0. Well, as x approaches 0, it's pretty easy to see that this denominator obviously is approaching 0. And this numerator will approach e to the 0th, which is 1, minus 1, which is also 0. So this is indeterminate of form 0 over 0, and we can use L'Hopital's. So using L'Hopital's rule, we get the limit as x approaches 0 of e to the x, that's the derivative of the numerator, divided by 1, that's the derivative of the denominator. Now as x approaches 0 here, you get 1 over 1, which is 1. That's pretty nice. So there is an example of an indeterminate form of 0 over 0, which approaches 1. Likewise, you could do the same thing in this next example, because again, the numerator is approaching 0, the denominator is approaching 0, so you can use L'Hopital's rule. Now this is actually just the reciprocal of the previous limit, so it's going to be 1, but I'm just showcasing this anyway. It's the limit as x approaches 0 of the derivative of the numerator divided by the derivative of the denominator. As x approaches 0, you get 1 over e to the 0th, which is 1. So those are some quick examples of using L'Hopital's rule on kind of easy problems. In the upcoming videos, we'll grow the difficulty of these and also showcase examples that lead to issues and students tripping up.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.